Here's our next problem. Please pause the video and try this problem. I hope that you gave that a shot. I hope that you actually paused the video and tried to carefully work out the problem. This problem is more difficult than the ones we did previously, so I hope that you actually tried to come up with a careful, thoughtful answer rather than just taking a guess. In some ways, this problem is very similar to one of the problems that we did in an earlier video. Notice here that we're dealing with a downward pointing vector f. But in this previous problem, we were also dealing with a downward pointing vector f. So does that mean they're the same problem? Well, no, they're definitely not the same problem, because remember that when you break a vector into components, the components depend on your axes. Notice that in the previous problem, we had horizontal and vertical axes. But in this problem, we have diagonal axes. So that's a big difference. Remember that components are a way to represent a vector relative to axes. So when you change the axes, you also change the components. So even though the vector in this problem is basically the same as the vector in the previous problem, downward pointing vector f, the components will be quite different because the axes are different. All right, so I hope that was apparent to you when you were trying the problem. If that wasn't apparent, maybe you should pause the video and try the problem again, paying attention to the fact that changing the axes changes the components. Well, let's try to go through that together. Now, I hope that one of the first things you tried to do was draw a right triangle to represent the components, just like we have on earlier problems. We need to draw a right triangle to represent the components. Now, of course, this problem already has a right triangle, but I hope it was obvious to you that this right triangle does not represent the components. This is a right triangle, but it's not a right triangle that represents the components for f. So we still have to make our own right triangle that represents the components for f. Well, this is one point where a lot of students would have difficulty. A lot of students would have a hard time drawing the right triangle that represents the components of f. Remember the method that we learned. The method is that the legs of the right triangle should be parallel to the axes. The legs of the right triangle should be parallel to the axes. So, for example, we should have one leg that's parallel to this x-axis. So we could try drawing through the tail here. Through the tail of the vector, we could try drawing a line that's parallel to this x-axis. Now, in this case, that line was already drawn for us in this right triangle. So this line here of the right triangle is already parallel to the x-axis. So we can simply take, this is the line through the tail of the vector that's parallel to the x-axis. And then through this point in the head of f, we therefore have to draw a vector, draw a leg that's parallel to the y-axis. Okay, so now I've done that. I've drawn this leg that's parallel to the y-axis, and what do you know? Now we have our right triangle. So again, I know this is a step that would give many students difficulty. Remember that you draw the legs parallel to the axes. Here we drew this leg parallel to the x-axis. That actually was right on top of the line that was already drawn for us. And this leg parallel to the y-axis. And then we got a right triangle. Then we can label the components. This was the side that was parallel to the x-axis, so the symbol for that would be f sub x. And this was the leg that was parallel to the y-axis, so our symbol for that would be f sub y. All right, and then we have to put in the arrows on these legs. That's very important not to forget. We need the arrows on those legs. That was another part that might give students difficulty. There's a couple ways to think about this. We can go back to the rule that we learned earlier. Here is that rule that we learned earlier. The head of a component arrow should be at the head of the overall vector, and the tail of a component arrow should be at the tail of the overall vector. So for example, here we have the head of the overall vector, so that should overlap with the head of the component. So I'll put the head of an arrow here to show that the head of the component is in the same position as the head of the overall vector. Now, over here on vector f is the tail of vector f. Well, where the tail of the overall vector is, that should overlap with the tail of the component. So these would both be vector tails, which means this must be the vector head for the x component. So that's one correct way. That's the most correct way, most systematic way to figure out where to put the heads and the tails of the arrows. The tail of this x component is where the tail of the overall vector is, and the head of this y component is where the head of the overall vector is. All right, notice that when you use this rule, you're comparing the component and the overall vector. Component and overall vector, component and overall vector. This is not applied to comparing the two components. We're not saying that, obviously we're not saying that the head of this component is where the head of the other component is. That's not the way the rule works. We're saying that the head of the overall vector is where the head of the component is. Now here's maybe a simpler way to think about this that I guess is also correct. The components are supposed to represent the overall vector. Well, therefore, since the overall vector points down, we would expect these components to also point down. And notice that they both did end up pointing down. F sub x ended up pointing down and to the right. And f sub y also ended up pointing down and to the left. But they're both pointing down, which makes sense since they're supposed to represent the overall vector, which points down. That's maybe a faster and more intuitive way to figure out the directions of those components. Now, remember there's always really two different right triangles you can draw for any vector. There's two different right triangles you can draw to break any vector into components. And for this problem, I think it'll be useful to draw the other right triangle as well, just so that you can choose which one you'd prefer. This is a perfectly good right triangle to draw, but for practice, let's see if we can draw the other right triangle. In fact, maybe now would be a good time for you to pause the video and see if you can do that. Try pausing the video and see if you can write the other right triangle that represents the components of f. So I should say, probably it's best not to do it in the same picture. We don't want to get this picture too messy. So let's try drawing the other right triangle in a separate picture. Our goal here is not to get this problem correct as quickly as possible, but to learn about the concepts while doing the problem. So we'll take our time and draw a new picture. So how can we draw that other right triangle? Well, remember that in this case, we drew a leg parallel to the x-axis through the tail of the overall vector. From the tail of the overall vector, we drew this leg parallel to the x-axis. The alternative is that through the tail of the overall vector, we can draw a leg parallel to the y-axis. So in this case now, through this point, I'll draw a leg parallel to the y-axis. So here I've drawn a line parallel to the y-axis. Through the tail of the overall vector, I drew a line parallel to the y-axis. Then to finish the triangle, through the head of the overall vector, I'm going to draw a line parallel to the x-axis. Through this point, I'll draw a line parallel to the x-axis, and where those lines intersect will give us our right triangle. Okay, through the head of the overall vector, I drew a line parallel to the x-axis, and where there's two lines intersected gives us the right triangle. Here's a line parallel to the y-axis, here's a line parallel to the x-axis. And then now I can erase this overlap. We should label the sides. Of course, this side is the overall vector, f. This side was parallel to the y-axis. So we'll call that f sub y. And this is the side parallel to the x-axis. So we'll call that f sub x. And again, we need to put on the arrows on the legs. Well, we can use the overlap method, where we have the head of the overall vector. We also want to have the head of a component. And where we have the tail of the overall vector, we should have the tail of the y component, which means this is the head of the y component. Or you could just say that the overall vector points down. And since the components represent the overall vector, each of the components will also point down. Fy points down and to the left, and fx points down and to the right. So those are the two possible right triangles. Here's one possible right triangle that we could draw to represent the components, and here's the other one that you can draw to represent the components. Which of those is correct? Well, either is correct. Whichever one feels more convenient to you is the one to use in this case. Some students might prefer this triangle, and some might prefer this one. It's really a matter of taste. Now, my experience is that most students initially cannot draw the correct right triangle to break this vector into components. Almost all students get this wrong the first time because they draw the wrong triangle. So what triangle do most students try to draw in this situation? Well, the problem is that on most problems, like most of our previous problems, we've been working with horizontal and vertical axes. So on most problems, you draw a triangle with horizontal and vertical legs. So most students are try to draw a right triangle maybe like this, with horizontal and vertical legs and a diagonal hypotenuse, just because that's the kind of triangle we've seen in the past. But I hope you can see why that doesn't make sense for this problem. Because remember, there's a few things. In our right triangle, the hypotenuse is supposed to represent the overall vector. Well, you can see this is wrong because here the hypotenuse is not the overall vector. Here this leg is the overall vector. That's one reason why this is a wrong triangle. You can see here we got that correct. In these cases, the hypotenuse was the overall vector. You know this is the hypotenuse because it's opposite the 90-degree angle. And the other important way to see this is wrong is remember that in the correct triangle, the legs are supposed to be parallel to the axes. The legs should be parallel or anti-parallel to the axes. Well, these legs are not parallel to the axes. These legs are horizontal and vertical, but we don't have horizontal and vertical axes here. We have diagonal axes. So you can also see this triangle is wrong because the legs are not parallel to the axes. All right, the reason people would draw this type of triangle is simply that, unfortunately, most students are kind of on autopilot when they're solving physics problems, and they usually just try to do each problem the same way as the previous one without always noticing whether the previous method applies. So don't be on autopilot. Draw the correct triangle where the hypotenuse represents the overall vector and the legs are parallel or anti-parallel to the axes. Components are all about the axes. So this is the wrong triangle for these axes. This is the wrong triangle for these axes. I hope you didn't draw that, and I'll erase that. If you did draw a triangle like that, that indicates that maybe you're too much on autopilot when you're doing these problems, and you need to try to adapt to the details of the problem more carefully. So the correct way to draw the right triangle is don't assume that the legs are horizontal and vertical. Instead, draw the legs so that they're parallel to the axes. And then you can adapt to whatever type of axes you're dealing with on the problem. All right, now if you were not able to draw the correct right triangle when you tried this problem the first time, maybe now that you see the correct right triangle, maybe now you should pause the video and try to complete the rest of the problem. All right, so let's go through this together. Now, are we ready yet to label the opposite, adjacent, and hypotenuse? Can we label opposite, adjacent, and hypotenuse yet? Well, we can certainly label the hypotenuse, as I already mentioned. We can say this side is the hypotenuse. Why? Because it's opposite the 90-degree angle. That's the definition of the hypotenuse, the side that's opposite the 90-degree angle. Again, this might feel weird because you're probably used to hypotenuses that are diagonal. You're used to a hypotenuse that's diagonal, but in this case, the hypotenuse happened to be vertical because that was the side that's opposite the 90-degree angle. And similarly, in this picture, this side is the hypotenuse. And I think in the rest of this problem, I'm going to be working with both of these triangles. Of course, in a real problem, you could just choose one of these triangles and work with it. But for the benefit of our understanding, I'll continue to work with both of these triangles now. Okay, but which of the legs should be labeled opposite and which should be labeled adjacent? Well, we're not ready to figure that out yet, because you should know that opposite and adjacent, as we've talked about, depends on which of the angles we're focusing on. Are we going to focus on this angle, or are we going to focus on this angle? Until we decide which angle we're focusing on, we don't know who we're going to label as opposite or adjacent. Now, the problem so far is we don't know either of these two angles. We don't know either of these two angles. So before we do anything else, we actually have to do some geometry. We do know one angle. We know this one. This angle was given to us as theta. Remember that if an angle is mentioned in the problem, we treat that as a given. So we're going to treat this angle as a given, but we need to use this angle to figure out one of the angles inside the triangle. And that's really not about physics, that's about geometry. Do you know how to use geometry to figure out one of these angles inside? Again, you might want to pause the video and see if you can use geometry to come from this angle to this angle. All right, well, let's go through that together. There's a few different ways to work out the geometry. I think the simplest way to work out the geometry here is to extend this vertical line down. I'm going to extend this vertical line down. That's useful because, do you see, now we've made a big right triangle. This is now a big right triangle, and that tells us that this angle and this angle, well, first of all, can we say that this angle is theta? No. There's no reason to assume that this angle at the top of the right triangle is equal to this angle at the bottom. There's no rule that the two acute angles in a right triangle have to be equal. So we cannot assume this is theta. So instead I'll just call it alpha. Alpha is just a symbol that I made up to keep track of this angle. So alpha is this unknown angle with a symbol that I made up. And the important thing to realize is, what's the relationship between alpha and theta? What is the relationship between alpha and theta? Well, we should know that alpha plus theta is 90 degrees, because those are the two acute angles of a right triangle. The two acute angles of a right triangle add up to 90. Because if we add this plus this 90, we have to get up to 180. Since this is 90 degrees, that leaves 90 degrees left for these two angles. So these two angles have to add up to 90 degrees by the rules of a right triangle. Okay, and then how big is this angle? Well, remember that now we can focus on this little right triangle. Remember that this little triangle is also a right triangle. Since this little triangle is also a right triangle, these two angles should also add up to 90. This angle plus this angle should also add up to 90, because these are, again, the two acute angles from a right triangle. But doesn't that mean that this must be theta? So we know this must be theta. If this angle and if this and this add up to 90, and this add up to 90, then these two angles are the same. I think you can see here that this angle here must be the same as this one. It must be theta. Okay, so now we know the two angles inside the right triangle, alpha and theta. And again, the trick that we used to figure that out is, first we drew this line down so that we could consider this to be a big right triangle. So we knew the relationship between this angle and this angle. They added up to 90. And then we thought about the smaller right triangle, and we knew that this angle and this angle also added up to 90, so we knew that this and this were the same. And we can try the same over here. Again, you might want to pause the video and see if you can figure out some of the angles in this triangle. Well, we can use the same technique of extending this line down, and now we can focus on this big right triangle. Well, I'll call this angle at the top alpha. And again, we know alpha plus theta is 90, because these are the two acute angles in the big right triangle. Okay, and now let's think about this angle. How big is this angle? Well, you should know the key here is that we know that this angle is 90 degrees. How do we know that this angle is 90 degrees? Well, remember, this line is parallel to the y-axis, and this line is parallel to the x-axis. But our axes are always perpendicular to each other, and therefore those lines are perpendicular, so that's 90 degrees. maybe that might be a slightly different, slightly more difficult thought process than on the previous case. I'll go through that one more time. This angle from here to here is 90 degrees. It's a right angle. Here's how we know. This line is parallel to our y-axis, and this line is parallel to our x-axis. But the y-axis and the x-axis are perpendicular to each other, and therefore these two lines are perpendicular, and that's a 90-degree angle. All right, but doesn't that mean then that alpha plus this unknown angle equals 90 degrees? Therefore, this unknown angle is theta. All right, so now we know that this angle is theta. You could go the next step and say that this angle is alpha. Therefore, although that's not going to be too important to us, we could also now figure out that this angle is alpha because these add up to 90. But for solving the problem, we can just stop right there. So now we've done the geometry that was necessary to figure out the angles inside the little triangles. That's a very important step. We did that geometry. That wasn't physics, that was geometry. There are a fair number of places in your physics course where you'll just have to use some high school geometry. So again, there's more than one way to use geometry to work this out, but I think the simplest is to extend this vertical line down so that you get a big right triangle. Okay, now which angle should we focus on in the triangle? Should we focus on alpha or theta? Well, you could focus on either, but it's going to be a lot easier to focus on theta since that's the angle that was specifically mentioned and given in the problem. So you'll make your life a lot easier if you focus on the theta angle and not the alpha angle. I'm going to put in a star here to remind myself that I'm focusing on this angle, theta, not this angle, alpha. And I'll put a star here to remind myself that in this triangle I'm going to focus on this angle, theta, not this angle down here, which would be alpha. That's why I didn't even bother to write alpha down here, because I'm not going to use that to solve the problem. By the way, when you do this geometry on your own, you might want to use this technique I'm using here of inventing a new symbol for the unknown angle of alpha. If you already have one angle of theta and another angle adds up with that to 90, it helps to give that a name and call it alpha. So inventing this new symbol alpha, I think, helped us to think more clearly about the problem, and that would be a good technique for you to use when you're thinking about similar geometry. All right, and now again, if you were stuck on this problem, maybe you should now pause the video and see if you can now complete the problem and figure out the components. Okay, so again, in real life, you would only have to use one of these triangles to complete the problem, but for practice, I'm going to show you how to use either triangle. So now we can label the opposite and adjacent sides. Remember, we're focusing on this angle here, so the side that is adjacent to theta is this. And the side that is opposite to theta is this. Remember that opposite and adjacent depend on which angle you're focusing on, and we decided to focus on this angle. So this is the leg that's adjacent to the angle theta that we're focusing on. This is the leg that's opposite to the angle theta that we're focusing on. Over here, this side is adjacent to the angle theta that we're focusing on, and this is the leg that is opposite to the angle theta that we're focusing on. Now we can use SOHCAHTOA to break things into components. As usual here, so we know this hypotenuse. I think I'll stop using the arrow here and simply say that we know the magnitude of this hypotenuse is given by the symbol F. They gave us this symbol for the vector, we know if this is the symbol for the vector, then the symbol for its magnitude is F without an arrow. So I'm just going to use F now without an arrow to show that now we're using this to represent the length of this side, or the length of this side. So since we know the length of the hypotenuse, we should use sine and cosine, because those are the concepts that use hypotenuse. So we have that the sine of theta is opposite over adjacent. Cosine theta. Oops, got that wrong. Sine of theta is opposite over hypotenuse. Cosine of theta is the adjacent side over the hypotenuse. While the opposite side is f sub x. And that's true in both triangles. In both triangles, f sub x is the opposite side. Now remember, this equation will only tell us the magnitude of f sub x, so I'm going to use absolute values for that. And the hypotenuse is, the magnitude of the hypotenuse is represented by capital F. Our adjacent side in both pictures is f sub y. F sub y here and f sub y here. And the hypotenuse again is f. And again, I'll use absolute value symbols to show that this equation is only going to give us the magnitude, the absolute value of the component. Oh, it looks like I forgot something, didn't I? I think I've recommended to you in the past that you should figure out the plus and minus signs on the components before you figure out the magnitudes. Otherwise, you might forget about the signs altogether. So let's go back and do that. I hope you did that when you were trying to solve the problem. While f sub x here is pointing in our positive x direction. So f sub x will be positive. And that's true in both of our pictures. F sub x here is pointing in our positive x direction. So we'll use a plus sign to show that that will be positive. And f sub y here, well, f sub y is pointing in our negative y direction. You see how this direction is anti-parallel. This vector is anti-parallel to the y-axis. So f sub y is going to be negative. So I'll go ahead and put that in. It's a good habit to figure out the plus and minus signs on the components before you figure out the magnitudes, because otherwise you might completely forget to do the plus and minus signs. All right, now I should have done that before I even started SOHCAHTOA. Now we can go back down to our equations. So remember here that on this problem, the givens are theta and f, because those are the symbols that were mentioned in the problem. If something is is mentioned in a diagram, we treat that as a given. So the symbol in the diagram here were theta and f. So we can treat those two symbols as our givens, theta and f. And we need to solve for the unknowns, which are the components. So we need to multiply both sides by f to get the component by itself. So the f's will cancel. Okay, so that gives us the magnitudes of the components. Now, remember, we were using absolute value signs here to remind ourselves that the SOHCAHTOA equations only give us the magnitude of the components. They don't tell us the plus or minus signs. So there's one more step where we figure out the complete component, including a plus or minus sign. And now that we're ready for the complete component, we use this symbol, not this symbol. Now we already figured out the signs. F sub x here we know is positive. And f sub y we've already figured out is negative. So as usual, one of the most common mistakes that students might make on a problem like this is forgetting this negative sign. So I hope that you were careful when you tried the problem to get the correct plus and minus signs. If we include a plus sign in front of our positive component, we're more likely to notice that this component is negative. Okay, so now we've done the key work, and we've broken this vector into components. So let me mention here, notice that in this case we used cosine to figure out the y component and sine to figure out the x component. And that we've done that sometimes in the past, but that's not the most usual pattern. The most usual pattern is to use cosine for x and sine for y. So this is not the most usual pattern, but I've already warned you about that earlier in this video. Don't assume that you always use cosine for either the x or the y component. Whether you use cosine for x or y depends on the details of the problem. So it's always best to go through this process of figuring out the opposite, adjacent, and hypotenuse sides of the triangle, and then writing out the algebra of the SOHCAHTOA equations. That way you'll know what the correct way is to figure out the components. As we've seen, you can't do this on autopilot. So now we're ready to fill in our table. In this case, we could say that the direction of the f vector is down. We don't need to use an angle to describe this direction. We can describe it with the word down. And then the f arrow, we already know, points down. Our f arrow points down. And then how are we going to represent? Remember that this symbol stands for the magnitude of the vector. Well, all we can say is that the magnitude of the vector will be represented by this symbol. We can't say any more than that, so I'll just leave it like this. This is a kind of improvised way of saying that we'll just use this symbol for the magnitude of the f vector. Now remember, this symbol with the arrow describes the complete vector, magnitude and direction. So we can say that this has magnitude f and direction down. When we write the f with an arrow, it means that we're describing all aspects of the vector, magnitude and direction. This is all stuff that we knew from the original picture, and now we're ready to fill in our components. So we determined here that f sub x was positive f sine theta. It's really a good idea to continue to write down that plus sign to show this is a positive component. And f sub y is negative f cosine theta. That's what we figured out in this problem. So the direction of fx, that's the positive x direction. So this is pointing in the positive x direction. It's a little hard to describe in words what this direction is. You don't just want to say that it's down and to the right, because that's not precise. There's many different directions that are down and to the right. One thing we could say is we could say that this is parallel to our positive x-axis. We could just say this is parallel to the x-axis. Something else you could do, though, is what we're really trying to get ready for here is this is the kind of vector and axes that you'll see when you're working on inclined plane problems, where this surface is the surface of an inclined plane. That's where you're actually going to apply this. So you could just say this is the pointing in the positive x direction. But I'm going to go ahead and interpret this as an inclined plane, and now I'll say that this is the direction down the inclined plane. Down the incline. We'll interpret this diagonal line as an incline, and then fx is pointing down the incline. All right, and then our fx arrow points in this direction. This direction, down the incline. And the magnitude of fx is f sine theta. Now I'm not going to include the plus sign, because magnitudes would never be negative. So there's no need to emphasize that this is positive. Let's go through a similar process here. So how would you describe the direction of f sub y? Again, that's a little bit tricky. You could just say that f sub y is pointing in the negative y direction, or you could say the direction is anti-parallel to the y-axis, or pointing in the negative y direction. That would be acceptable. But if we interpret this as an inclined plane, we can say that f sub y here is pointing, I guess, into, maybe we'd say that it's perpendicular to and into the inclined plane. Clearly this direction is perpendicular to the inclined plane, and it's not pointing away from the inclined plane, it's pointing into the inclined plane, if you think of this whole triangle as a solid object. So that's maybe not an ideal way to describe it, but of course we'll accompany that with this picture of the arrow, and the arrow makes it clear what the actual direction is. So that's one way we could describe this. Or again, you could simply say that the direction is in the negative y direction, or anti-parallel to the y-axis. That would also be acceptable. Now the magnitude of f sub y here is f cosine theta. Magnitudes are never negative. Okay? So now we've worked this out. I hope you can see that all of these equations would apply just as equally to the left-hand triangle or to the right. These would be the equations we would use for this triangle or for this one. And again, when you do this problem, when you dealt with this on a real problem, you would only use one of these two triangles, whichever you prefer on the left or the right. But I drew both of them so you can learn how to use either. And now we filled out our table of answers. Okay, so like I said, this might have seemed like a weird problem. Certainly it was more difficult than the earlier ones, but this is actually something you're going to need to do a lot pretty soon in your class. Pretty soon in your class you're going to be working on something called inclined plane problems. And this situation, where you'd have to break a vector like this into components, comes up every time on an inclined plane problem. So this is definitely a skill that you will need pretty soon in your physics class. And I hope that even if this was challenging for you, you can review the problem and practice it so that it gets to the point where it's boringly easy for you. So let's review the key things that might have given people difficulty here, or the key ideas that we need to have. The first most important thing is don't be on autopilot. Don't just assume that things will come out the same on this problem as on earlier ones, but work it out step by step. The main reason this problem is different is because the axes are different than what we've seen before. Usually we use horizontal and vertical axes, but here we're using diagonal axes, and that changes things because the components are based on the axes. Remember, we already did a problem with this same vector with horizontal and vertical axes, so you might want to compare the results here. Here's how we broke a downward pointing vector into components using horizontal and vertical axes. That was very easy, and we didn't even have to draw a right triangle. And here's the more difficult case where we broke a downward pointing vector into components using diagonal axes. That was a lot more challenging, and we had to draw the right triangles here. So the first step here was drawing the right triangle. And remember, don't assume that the triangle looks like this. Don't assume horizontal and vertical legs. Since the axes were diagonal, our legs were diagonal here. Draw the one leg parallel or anti-parallel to the x-axis, and draw another leg parallel or anti-parallel to the y-axis. That is the correct way to draw the right triangle. But then after we drew the right triangle, we had another problem, which is that we had to figure out some angles inside the right triangle. And in my experience, students almost never do that the first time they see this. What students do is they always just kind of try to use this angle and just take a guess as to how it applies to this triangle. Students almost never realize that knowing this angle is not enough to start breaking this into components. This angle does not help us to break the vector into components because we need an angle inside this right triangle. So what we had to do is use geometry to use this angle to figure out the angles inside the right triangle. And by doing that, we were able to figure out that this angle was theta, or that this angle was theta. Remember, a useful technique there is to label this angle as alpha. Obviously, this would have been a little bit easier if you'd had a numerical value. I hope it's clear to you that if you knew a numerical value for theta, you could use, like, say, 20 degrees. It would be, you could use a similar but somewhat easier technique to figure out that this angle is 20, and that this angle is 20. And of course, this would be 70, and this would be 70. It's a little bit trickier when you're given a symbol rather than a number. But I hope now we understand how to do that. Physics, you just have to use some high school geometry. Okay. And then once we figured out these angles, we had to make sure that we kept in mind that that was the angle that we were going to focus on, the angle of theta, and then we labeled opposite, adjacent, and hypotenuse, and we're able to do the normal SOHCAHTOA equations. If this problem gave you difficulty, I'm not gonna do another example like this, just because I don't feel like it. But if this problem gave you difficulty, I suggest that you should now just pause the video and do this problem again from scratch. My experience is that probably very few students watching this video got this right the first time. If you did get this problem right the first time, fantastic. That shows that you've really picked up a good understanding of the material. But if you're in the majority of students who did not get this right the first time, you should now just pause the video and do this problem again from scratch. Again, remember, don't just remember the previous answer. Go through all the steps of solving this step by step so that you can practice how to break a vector into components when we're using unusual axes. You want to get to the point where this problem is boringly easy, because this is still not supposed to be the hard part of physics. Vector into components would just be one small step in a longer inclined plane problem, so it's important that you can get through this quickly and with confidence.